Okay, 5 and 6, last two on 4B. This is the table. We have a little chart. Summarizes age at diagnosis and gender, man or female, for schizophrenia. And they give you the charts, and they also give you a little picture. Why they give you this picture, I don't know. It says, does the data provide convincing evidence? This kind of looks like it, but we've just seen other problems where it looks like it's not without the data. So this is a straightforward chi-square test of independence. Just a quick reminder, simple random sample, one population, two traits, each expected value is greater than or equal to 5. So remember on this one, you're going to put all these data points in to your calculator in matrix 1, then just go run the test. The test is going to ask you for an expected matrix. Don't do it, just run the test and then go back to the matrix, and it's going to give you all these expected values. They're all greater than or equal to 5. The null hypothesis is there's no association between gender and age group, or you can just say gender and age group are independent, works the same. The alternate is they're not independent. It's a right tail test always, because it's skewed right for chi-squared. 7.81, 3 degrees of freedom. This is a 1, 2, 3, 4 by 2 chart, so 3 times 1 is 3 degrees of freedom, 7.81 for the critical value. But all you gotta do is put this matrix in the calculator, hit the button. You get 10.88 for your chi-squared test statistic, p-value of 1.2%, small p-value. You're going to reject the null, which means there is evidence of an association between gender and age group. And number 6. It's going to be hard for me to explain number 6. This tree diagram could have been gigantic, and I didn't really want to write the whole thing. I was going to try to explain it. This is the one where you got 2 men, 2 women, and you're going to put them in groups. 2 people go into treatment, 2 people go into control group. So they just told you all 6 ways that could happen right here. And then they said, let's talk about how we might do it. You could certainly put names in a hat, pull them out, that kind of stuff, right? The first one is the coin flip method. So let me try to explain how I got these numbers. And when we assign, we're always going to assign man 1 first, man 2 second, woman 1 first, woman 2 second. So let's just go for arrangement A. If the first guy is going to wind up with the treatment, he's got a 50-50 chance of that, so that's a 0.5. And then the second guy comes along, we're going to flip a coin, he's got a 50% chance, so that's 0.5. So you just go 0.5 times 0.5, gives you 0.25 for the 2 men here. And then in D, it's actually the 2 women in one group and the 2 men in the other group, same thing, right? 0.25. But for the other groups, where there's 1 man and 1 woman each, there's a 50% chance of the first man, but then you got to do a 50% chance for the second man being over there, and then a 50% chance for woman 1 being over here, so 0.5 times 0.5 times 0.5, hence all the 0.125s. You could draw a little diagram for that, but it's going to make more sense on the next method. And the question was, what's the probability that 2 men are together? 50%, right? They're both together in this one and in this one. This one's a little bit more difficult. This is the coin or the chip method. We just have 4 chips basically. It's just the same thing as putting names in a hat in essence. 2 are marked treatment, 2 marked control. The first guy picks it, the next guy picks it. This is different because now there is no replacement, right? That chip stays out. Whereas in the coin flip method, replacement, the 50% chance every time. So I just started a tree diagram. It's gigantic. But the same thing happens. So the first man has a 50% chance he's going to pick first. He's got a 50% chance of getting treatment or control. Now the second man comes along. If the first guy got the treatment, there's now only 1 treatment chip left. So the second man's chance to get a treatment is 1 out of 3. To get the control, it's 2 out of 3. Now the woman comes along. If the first guy got a treatment, the second guy got a treatment group, the third woman can't. She's got to get in the other group, right? So you can see this. And then if you go down here, treatment control, now there's 2 chips left, so 50% chance. The last person's just, there's no probability at all. It's either 0 or 1. So if you add up, or you just multiply this times this times this times this, you get a bunch of zeros, because some groups are just impossible. You can't get treatment, for example, so you get 0. Anytime there's a 0, you're going to get a 0. If you just go 0.5 times 0.666 times 0.5, you get 0.1665, and there's going to be 6 of those. They're all going to be the same. They're going to occur in a little different orders, but they're all going to be the same. Now the question is, what's the probability that 2 men are together? Same thing, groups A and D, so just multiply those by 2, 33% chance. And the last one says we got 16 people consisting of 10 students and 6 teachers. How should we group them? The chip method's the better way. just because it doesn't replace. It's always better when you don't replace. There's a lot less likely chance to get an overload in one group, as you can see here, right? More likely to get 2 men, not as likely to get 2 men. So same thing, the more you got, the more likely it is to get an overload if you're flipping a coin, but not an overload if you're using the chip method. So that's it for 6.